Good morning, everyone. We should have more people coming in. They're just they rang the bell upstairs, so hopefully we'll have more clients in our room. Bonjour à tous. Je vous souhaite la bienvenue au workshop numéro 6. I'm sorry, we'll have to go in English now. So we have to introduce in French because we're in a French province. So I welcome you in my hometown, Quebec City, for the 10th International Conference on Concrete Pavements. Thanks for participating in this workshop on precast concrete pavements, sponsored by the National Precast Concrete Association. I saw that they put some paper on your desk, so please take a look at them, and you can keep them, of course. There's a website that you can go also on internet. So my name is Denis Thibault. I work for the Ministry of Transportation of Quebec, and I work in the central office for pavements. My main work is design, rehabilitation, and construction of concrete pavement. So when Mr. Smith asked me to chair this workshop, I was pleased to accept, since MTQ has an experience with precast concrete pavements. This is in 2008. This was part of a reconstruction project of a concrete pavement in Laval, north of Montreal. In that project, the approaches of a bridge were narrow, so 8 years before, we had to rebuild the concrete pavement south of the bridge, and with the conventional method. And in total, it took like over 1 month per direction to rebuild the approach, the south approach. We then decided to try the precast slabs in 2008, and we were able to install around 100 slabs in each direction in 2 weekends. Unfortunately, no other precast slabs were installed since then, even in maintenance projects, but we're still pushing this option in the regional office. Like I said, I am in the central office, so I can do some recommendation, but I don't have the money. But still, we try to push this hard in the regional offices. I hope that this workshop gives us a good update on this interesting topic, and hopefully helps us to find ideas to convince the managers to use more frequently the precast slabs in construction and maintenance of concrete pavements. Of course, we will hear from practitioners this morning, mainly from DOTs. We will have an introduction, the historic, international, and future perspective. A contractor will give us his perspective, and we'll close the presentation with an interesting use. We will close the workshop with an interesting use of precast slab. I think this is a futurist, I think. So please note that there's 2 changes in the program. We will not have the New Jersey perspective. Hello? Okay. We will not have the New Jersey perspective, and Mr. Niraj Bush accept to replace Shiraz Tayyabji for the second presentation. So just maybe 2 or 3 other things. I will ask all the participants to close their cell phones, of course. Each speaker will have 20 minutes, except the first 2 presentations. They have 30 minutes, so they have a bonus of 10 minutes each. We should have time at the end of the workshop for panel discussion around 11 o'clock if we're on time. So you can ask questions after each presentation, so keep them maybe 1 or 2, and after that we can wrap up at the end of the session. We plan to take the break around 9:40, 9:45, something like that, for 20 minutes. So I talked a little bit too much, so let's start now. So our first presentator or speaker is Mr. Ernie Barenberg from University of Illinois. Mr. Barenberg obtained his PhD degree at the University of Illinois at Urbana-Champaign, Illinois, where he taught and conducted research on transportation facilities for over 40 years. Dr. Barenberg's primary fields of interest are concrete pavements, paving materials, and railroad track systems. Recently, he has working He has been working with fabricator on the manufacture and installation of precast slabs for the repair and replacement of concrete pavement with minimum disruption to traffic. Dr. Barenberg, the floor is yours.
Thank you, Dennis. It didn't save me this morning. I was going to start off here by saying I'm getting too old to be doing these things because I couldn't even spell my name right. I had my name up there wrong and had an extra letter in it, but he saved me by taking it out. But I thank you for that. So let's see, my changer is right here. What do I do to change the? I can do it here. That's what I thought too. Ah, very good. That's probably easier for me to do it just right there. Precast slab has been around for a good number of years. My first experience with it was in the early 70s. I was working with a consultant, and my primary interest at that time was load transfer devices, but we put some precast slabs in on the Lindbergh field in San Diego. And that was in the early 70s. So that's 45 years ago that we started using the precast concrete slabs. They perform very well. We put it in with a grout, a plastic grout, had weep holes in it, and put the slab down and ran a roller around the edges to finally level it up and then let it set, and that worked out, and then came in later and put in some devices around it. Since then, I've gotten involved in a number of projects. Most of my work has been with the Fort Miller Group out of New York, but I have had the opportunity to work with a number of other precast pavements, including St. Louis, where we put in some individual pre-stressed slabs and some other innovative things. First of all, we'll talk just a little bit about what is the advantage of precast slab. One of the things that isn't mentioned very often, when you go out and you have a pavement and you say, it's distressed, we got to repair it. If you'll do a careful check, you probably find that less than 20% of that pavement has actually failed. The rest of it is in good condition. And the failures usually accumulate in areas, whether it be from construction, whether it be because of support, or climatic conditions, I don't know, but you'll find that they're clustered in very many months. I remember years ago when we were developing design procedures and we were talking about saying, well, if 20% of the slabs failed, the pavement has failed, and somebody said, oh no, it's much higher than that. Said, go out and look at this pavement, which we did, and we counted, and it was 14% of the slabs that had cracked. The rest were in pristine condition. So you're throwing away all of that good pavement if you take out the whole pavement and replace it. So why not save that, both in terms of material and in terms of cost, and just take out the parts that are distressed and then replace them. So that's probably one of the big advantages that I don't hear people talk about. So that's one of the things. Secondly, traffic these days, as Peter was saying last night, it took him 2 hours to get in from the airport. If you'd have had a construction on top of that, it would have taken him forever, days to get in. So this is something to prevent the traffic tie-ups, and that's one of the big reasons it is generally used. It can be placed in unfavorable weather conditions, and that, I think, is a big item. A lot of people are recommending the use of high early strength concrete, but you get bad weather conditions and you tie up that high early concrete and you get a truck that you can't dump, and you've got bigger problems than you started with in a long way. So you can put this in unfavorable weather conditions. I remember talking with some one time, asking how they were doing, and it was snowing. They said, it's all right, we put down 30 slabs last night. So you don't have to wait for perfect weather conditions. You can do it in all kind of weather conditions. Was out on one job where a big thunderstorm came up in the middle of the afternoon, and they just poured rain for about an hour. When it was all over, they got the pumps out, pumped it out, and went ahead. So that's a big advantage. And then the other advantage is that the curing condition on your slabs can be ideal, because these are all cured under laboratory conditions. Let's talk just for a little bit about what types of precast slabs that we can talk about. The most common, of course, is your jointed reinforced. And this can be plain reinforced slabs, where you just, as you all know, have some slabs, use ordinary reinforcing steel, and you put them in, and you have a reinforced slab. There have been a few of them placed with fiber reinforced, and I like that idea. I think that's going to be a coming area of the fiber reinforced. I know I've used some fiber reinforced. One of my colleagues at the University of Illinois has done a lot of research on fiber reinforcement. Works with, as a matter of fact, my house is built out of fiber reinforced concrete. So I am familiar with that one for sure, and it has worked out very well. I think I have one crack in one slab, and that's the driveway, the basement floor, the sidewalks and everything. And that's the only crack that we got out of it. So fiber reinforcement can be a very good thing to use. Two types of fibers. You can use steel fibers or polymer fibers. Steel fibers are harder to use. They can be very effective. We put down a pavement on an airport in Rockford, Illinois, a number of years, 1994 it was, and it's pre-stressed in the longitudinal direction, and fiber has fiber concrete, and then we post-tensioned it. And that slab is 1,200 feet long, 75 feet wide, and does not have an active joint in either direction. That's an impressive looking slab. Been down since '94. And we used the steel reinforced fibers, and we did not pre-stress it in the transverse direction, and the fibers were enough to keep it from cracking in the transverse direction. And then the longitudinal direction, of course, is the pre-stressing on that. So you can do some really innovative things if you use the fibers in conjunction with the other types. And you can combine these, like you can put in fibers with ordinary steel, you can use fibers with pre-stressing steel, etc. There is a pressure on, a lot of stress on for using pre-stressed, and it can be a good thing. As I said, we had good luck with pre-stressed on a number of occasions, but on the other hand, it should choose its location where you use it for the right conditions. And that is a discussion we could spend all morning on, so I'm not going to get into a whole lot of detail here, but just want to say that look at it, make your decision, decide whether it is worthwhile to you go to the route of pre-stressing, and get somebody who knows what they're doing, because that's the first thing that you're going to find out. I remember the first job I was on, and we wanted them to do some initial pre-stressing, and it had occurred in the middle of the night, and the worker said, oh, well, I can't do it because the bars extend and I can't extend them enough, so we've got to wait till morning where I can get a saw to saw them off. No, you stop them right there and says, whoa, stop right there. Put on as much as you can, and then we'll saw them in the morning. And so you got to have somebody out there that can take care of things as they come up. This is true of whether you're dealing with pre-stressed pavement or whether you're dealing with ordinary precast concrete. When you're doing with pre-stressed slabs, generally you will have a larger area you want to deal with, because individual slabs you generally don't need pre-stressing, although if you for some reason cannot put in an ordinary thickness, you may want to pre-stress it. But generally pre-stressing is not something you want to do if you're putting in single slabs. You want to have an area where you want, for example, a bridge if you have an approach to a bridge where you have non-uniform support where it goes out maybe 100 feet or so, that might be a candidate for a pre-stressed slab, because the non-uniform support, the pre-stressing can handle that better than the ordinary. So that would be a possibility to think about. And of course, if you have an area where you cannot put in the ordinary thickness, then you may want to think about that. When most of my rest of the presentation is going to deal with just jointed reinforced slabs. We can have either continuous multiple slabs, as many of them have been. The Tappan Zee is a good example. You can put in isolated slabs. A lot of the work they're going in now and just sawing out joints, 6 to 8 to 10 feet of sawing out the joint and dropping in a new slab that are precast. That slab that worked out very well. So a good use of that. For the most part, our slab would be flat slabs. However, I don't know if you realize how many slabs are actually warped. Sometimes when you think, when you go out a slab and say, oh, that's just a flat slab, you measure it, you may be surprised. It may be a warped slab. About 40% of the slabs out there are warped, and anytime you have an intersection or a curve, you're guaranteed to have a warped slab. So if you want to build these, you've got to be able to put in a warped slab. If you don't, you're going to have a rough pavement. So being able to put in a warped slab is a good thing. Define a warped slab as when one corner is 1/8 of an inch or more out of the plane of all the 3 other joints. That's just a kind of an arbitrary definition, but it can be as much as 2 inches up from that plane. Again, they occur at intersections, et cetera, and on curved ramps and all that sort of thing. Design of precast slabs. One of the first questions I often get asked is, how do you design a precast slab? And you get to talking with them a little bit, and what they're talking about is, how do I determine the thickness? Well, that's the one thing you don't do. That's preset. That it depends on the thickness of the pavement that you're repairing. Your slab has to match the existing pavement. You don't want to go deeper and dig down deeper than you were before necessarily, and you certainly don't want to be shallower. So the thickness is not there. Design involves many things besides just determining the thickness of a slab. And that can be the type of repair of support that you're going to get, the joint design, how you're going to place it, just many things. It's the whole picture of the whole thing. That's what design is all about. When I was as a young student, I had a mentor that I was really impressed with. I don't know if you know the name of Dr. Ralph Peck. Some of you, I'm sure, know that name. But he used to say, when you start a design, you probably know the answer before you start. What you do, your calculations, is just to validate what you've designed. And so the same thing with the slabs. You know what you want to put in there. And all of your other calculations and things are just to validate and verify that you have not messed something up. Now, there are many different types of bedding support, and bedding is one of the important things. The original precast, as I mentioned, was a kind of a fluid cement grout where you put it in, and you took a grout and then you put it in a little high, and you put your slab on. You had some weep holes in there, and you vibrated it down to the right level and let the excess grout then come up through the weep holes and around the edges. That works well, but it also has some problems. Foam polymer, the Urotech procedure, is another way of getting a good uniform bedding, where you put in the foam, and you can use that also to level the slabs, as well as providing a uniform support underneath the slabs. The one that is most commonly used is a well-graded, fine graded kind of a sand or gravel, and that is a stone dust. And this can either be stabilized or unstabilized. This is one of the things we keep getting arguments about. Should it be stabilized or unstabilized? We put down an awful lot of them that have not been stabilized. People worry about the pumping on that. It is a concern, and we've seen evidence of movement, but we have not had any failures that I know of as a result of pumping. So say, okay, we got to solve this problem. Maybe it's a problem, maybe it isn't. Conceptually, it is. Actually, I'm not sure that it is. The fine graded sands can be placed with great precision to the nearest 16th of an inch in elevation with using laser controlled screeds. At least that's what the Fort Miller group does. And they can also do this for warp slabs, where you actually warp them exactly to the shape of the slab that you're going to put in there. And that's a big advantage of that. Uniformity of support is a major concern. All non-pre-stressed slabs not placed on liquid grouts require some sort of a grout underneath to give a uniform support. As we've known from the time we started to design pavements, it isn't the level of support that's critical, it is the uniformity of the support that is the most critical. And that is true of precast slabs as well. We must develop a uniform support. So to make sure that we get it, we grout underneath that. And again, you use gaskets and things, and you pump grout underneath it to get you a nice uniform support under there. This can be distributed through channels that are built into the slab on the inside, and with gaskets that prevent the grout from moving all over and all. And the nice thing is that with these fine sands, excuse me, you can allow traffic on them before you do the grouting. So you can put the slab down one night, come back the next night and do your grouting. And that gives you a big advantage there. With pre-stressed slabs, they're usually placed on graded stabilized subbases and no grout underneath. Pre-stressed slabs can span some voids underneath easier than non-reinforced. Depends on the size of the void that you have. So you got to take a look at that. But they usually do not grout underneath the pre-stressed slabs. The next thing to talk about a little bit in design is the use of joint design. Urtech had a procedure where they used ties and put them together, and they tied the slabs together. They ran into some problems with cracking with that because they didn't get any movement. So again, something to be a minor detail. The reason we use dowels is so that the joints can open and close. Not a big mystery. We've known that for years. So it's just something to keep in mind. The dowels can either be grouted in from the top down by the slots that you go in there and cut the slots and drop your dowels in and fill them with grout. Or you can have a slot from the bottom and have holes and grout from the bottom up. Then you don't have the slots that are in the pavement. And those have worked out very well and been very effective. With pre-stressed slabs, you have joints, and I'm not going to talk much about that, but the pre-stressed slabs, the joint design depends on how long a stretch you have. If you have stretches of 400, 500, 600 feet, you need big major joints. If you have a couple hundred feet, why, maybe an ordinary expansion joint will do the job. So that's a individual design problem that you have to address. Probably require a special design. Like I said, the slab that we built that was 1,200 feet long, at the ends, that thing moves 5.5 inches every year, open and close from one end to the other. So you need a good joint, not just a dowel joint there. You need finger joints of some kind to allow you to that. So what kind of joint you need depends on how long they're there. Non-pre-stressed slabs, that's the ordinary reinforced, have been in service for many years and given good performance. They've done a number of accelerated tests. I don't say they've never had a failure. They've had some, and it can be for various reasons. It can be for construction. It can be for temperature. It can be for many reasons. But they tested a number out in California. I don't know if we have any Californians here, but they tested a number of them under their accelerated testing programs, and they got hundreds of millions of equivalent 18-kip single axle loads on these pavements without failures. So they can give outstanding performance where they're put in properly and outlast the rest of the pavement. The details of the load tests are in a paper that was presented down in the ISPC meeting in Rio. In what year was that? I forgot the year that was, but that was the conference preceding this one. And anyway, there's a paper in there that gives the details of all that precast testing. There are still many potential uses that have to be addressed, issues to be addressed on the use of precast slabs. Most of these are minor, none are debilitating. Most of these are very minor, but nonetheless, one has to pay attention to these details. And among the other things that I think really needs to be addressed is to, maybe we need to find and license contractors to do this and make sure that they know exactly what they're doing, because so many times some contractor says, no, I know how to do this, don't tell me, I can know better than you. Well, maybe they do and maybe they don't. So I think we ought to maybe think about having some licensing to make sure that we get people who really do understand how and when and what things to look out for. As far as the future for precast slabs, I think that's limited only by the imagination of the people who are dealing with it. You can do a lot of things here. As I said, you can combine different types of steel, different types of support, and just go on and on almost in ad infinitum and do many things. While the cost of precast repairs is more than for conventional repairs, it's not excessive, will continue to fall as more use is made of this technology. One of the big costs, of course, always is going to be transportation of the precast slabs. Maybe we need to think about setting up shops to do the precasting closer to the site, where you can do the precasting. If you've got a large number of slabs, maybe you need to have a plant or a place to ride on. For example, on some of the airports, they always have a lot of space that's available. So you could set up a plant out there and put your slabs up right on the site. The other thing that you have is a problem of slab size when you have to haul things over the road. If you have a site where you don't have to go over the road, you can make bigger slabs. You also have the limit of the slab size in terms of weight, so both size and weight. So there are many things like that that can be done to decrease the cost and make it more convenient. With that, I think I'm going to let it and answer any questions that you might have. Again, the details on many of these things you will get in the rest of the workshop, and that's why I didn't put it on. I've got about 500 slides I could have shown. I decided why delve into that when others here are going to be doing it. So that's why I didn't put up any of those slides to do it, and figured, well, let the other people do that, and I'll just leave it there. And if you have any questions, I'd be glad to answer any questions if you have any. If not, thank you.
Thanks a lot, Dr. Barenberg, for giving us a good overview of precast slab. So we will go to our next speaker, Dr. Niraj Bush. Dr. Bush is a professor and interim chairperson in the Department of Civil and Environmental Engineering at Michigan State University. He had his PhD from Texas A&M University. He will present us an overview of RO5 and international perspective. Thank you.
Thanks, Denis. As Denis mentioned in his opening remarks, I'm pinch hitting for Shiraz Tayabji, who is a little bit under the weather and has had to head back home. The good news is that he and I were co-PIs on this Strategic Highway Research Program, R05, on modular pavement technology. So I've been working quite closely with him over the last 3 years on this particular project, and have been working with precast pavements since about 2000. And my first experience was with Michigan DOT and the installation of some of the full depth repairs on some demonstration projects with MDOT. So what I'm, as it says in the title, the original presentation was prepared by Shiraz and it was emailed to me Monday night. But I had to modify it a little bit so that I could reduce the size, but couldn't reduce it as much as I would have desired to. So I'll try to talk a little fast and go through some of the slides that Ernie has already mentioned. The basic outline for the presentation is sort of give you an overview of precast concrete pavements, both jointed as well as the pre-stress technology. Talk a little bit about the U.S. and the international experience and just show you some examples. And I know the speakers following me are going to talk about specific experiences both in the United States and in Canada. And then also we have a presentation from Singapore. And then talk some specifics about the Sharp 2 products that have come out as a result of the modular pavement project R05. So basically, the definition of a precast panel is that it's fabricated off-site, transported, and more importantly, it's a rapid renewal strategy, which causes very little or minimal disruption to traffic, because a lot of the work that at least I witnessed in the last 12 or 13 years has taken place over weekend closures and as well as overnight construction. So that has helped in alleviating some of the traffic disruptions that can take place. It is a long life alternative, and by that what I mean is it has, if done correctly, as Professor Badenberg mentioned, it has about a 40 plus, 50 plus year lifespan, if done correctly. So it is long lived and has long life performance potentials. As the technology is being refined, the production rates have gone up significantly. I've been on projects where only 3 or 4 slabs have been installed in a 10-hour work window, all the way up to 50, 60 slabs being installed in a work window. So I think it's a combination of knowledge, technology, as well as the comfort level that the contractors experience once they have place these panels over a few work window nights, and then they get really comfortable, and then it's just like an assembly line when they start dropping these panels in and moving along. So this technology is coming along really well, at least in my opinion. The applications, as Professor Badenberg mentioned, they've been used for intermittent repairs, and that is just a fancy way of saying full depth repairs. So you can drop in individual panels, you can repair a crack, repair a joint, excuse me, put down a 6x12 panel and move along. There have been shorter length repairs where this is sort of a pseudo-continuous repair where you string along maybe 5 or 6 slabs together. And then, of course, there have been longer length multi-lane repairs where you're stringing or the work lasts for multiple work nights and you may have 50, 60, 100 slabs that need to be installed. So this is a very versatile method. Whether it's a jointed system or whether it's a pre-stressed system, it is a very versatile methodology for rapid renewal of concrete pavements. And the good news is that this is a proven product. The building industry, the bridge industry has been using precast elements for several decades with high performance and proven technology. So why not use it for concrete pavement repair and rehabilitation? Because we do have the working knowledge for this kind of technology. The other system, which is the pre-stress system, was originally sort of developed in Texas, and the first project, or the first demonstration project, was in Georgetown, Texas. I would say at least 10 or 15 years ago, and ever since the system has been evolved, and there have been several demonstration projects, and I think the most recent one was the Highways for Life project in Deland, Florida, where it was used as an overlay, as an unbonded overlay. So from going from conventional slabs, it has gone now to putting down unbonded overlays. So clearly the technology has matured as our knowledge has matured, as well as there's been performance data. And there are several versions of this pre-stress system. In many instances, in the most recent instance in California, in Oakland, the slabs were pre-tensioned in both directions and then post-tensioned. In many instances, the slabs were just post-tensioned, and everything in between. So this is another very maturing technology and a very useful technology in rehabilitating and repairing concrete pavements. As part of the R05 project, we recommended multiple refinements, and some of these haven't been tried yet. These are really paper ideas yet, and we're looking for ways by which these could be tried, at least at a trial level, and then if there is some level of success, they can be rolled out for production application. And these are sort of incrementally connected precast systems, so these are individually pre-tensioned slabs that then get hooked on with deform bars. So it's almost like a pseudo JRCP system with active joints at maybe every 60 to 100 feet long. Again, we don't know how this is going to perform because we really haven't tried these or installed these. Conceptually, they should work, but we'll have to see when they're actually installed and what are the construction challenges that go with it and the fabrication challenges that go with it. But again, this is another tool in the toolkit of a DOT that is looking for rapid renewals and rapid renewal strategies and long life strategies. This is just a picture of, the top picture shows you this is the Fort Miller system that Ernie just referred to that was used in Minnesota. This was a continuous application of jointed panels. And the picture below is an application of the pre-stressed precast system that was used in Delaware a few years ago. Here, the pavement was structurally was sound, but it was the joints had deteriorated due to ASR, and this was a project where the Delaware DOT chose to use the pre-stressed precast system. And I recall I was at this demonstration project, and it was. It is quite interesting to see how the operation works and how these panels get installed in a night closure. And this pavement is performing just fine because we've done some distress surveys and we've done some load transfer testing on this, and these pavements are performing just fine. And so they're living up to the expectations as far as we know. This is another project in Virginia, I-66, on I-66 in Virginia, where both the precast system, the pre-stress system and the jointed systems were used at different parts along this project a couple of years ago. And these projects are working reasonably well. And again, this was, as you can well see, the level of traffic that exists on these interstates. So a lot of the work was done at night as far as this project was concerned. This is a project on I-680 that I just had mentioned in California. This was done last year, and this was another testimony to the installation of precast panels, both jointed as well as pre-stressed precast panels. And again, I had the opportunity to visit this project and actually observe the installation and the construction of this I-680 project. And yesterday, I don't know how many of you were at that presentation in technical session 4. Tinu Mishra from Caltrans presented the innovations and presented the example of how a contractor, how an engineer, and how an owner agency partner and essentially implement installations almost on the fly, innovations almost on the fly, and all indications are that this project was a success. So again, this is another example of the application of this rapid renewal strategy. I'm just going to show everything here. There are several technologies out there. Some are proprietary and some are not. The precast pre-stressed pavement system, whether we call it the FHWA system or the Texas system, but that's not critical. The issue is that this is a maturing technology. It's a non-proprietary open source system that can be used. Some other non-proprietary jointed systems is the one that we developed in Michigan about 13, 14 years ago. There's an Illinois tollway method, which is probably a refinement on the Michigan system that was developed, as I said, a few years ago. There are proprietary systems like the Fort Miller system, the Roman stone system, and one out of Hawaii, which is the quick slab system. And all these, at least the Fort Miller system and the Roman stone system and the quick slab system have applications, both intermittent as well as continuous applications. I would suspect and submit that the Michigan system is more limited to the intermittent, isolated, full depth repair applications. I don't think we've never used it for continuous repairs. The Illinois tollway system, as I said, is really a reincarnation or a refinement of the Michigan system and has only been used, as far as I know, on sort of intermittent kind of repairs, not on continuous repairs. But nonetheless, all these systems, if further refined, can be extended and expanded to any and all kinds of applications in precast technology. The PPCP system or the pre-stress system basically consists of multiple slabs, and this is an older set of slides where you have these key joints. The distressed concrete is removed. Several base types have been used. Hot mix asphalt bases have been used. Pervious concrete bases have been used. Rapid setting lean concrete bases have been used to fill up the elevation difference. And then a bond breaker is placed. In this case, you can see plastic sheeting that is placed, and then these pre-stressed panels are placed. These pre-stressed panels in this particular picture are 36 feet wide and 12 feet long. And I-680, they sort of turned it around. They only made it 12 feet wide, but they made it 36 feet long. That allowed for them to do rapid construction and install several panels in a given work window night. So again, that's an example of innovation that has taken place. But the bottom line is, as I said, this is a very versatile system where you can, if done correctly, you can really accommodate what the job needs are and what the specification needs are. In this case, you are seeing that the post-tension blockouts are on the surface, whereas on the I-680 project, they were post-tension from the ends or from the sides. So again, that was another modification to the PPCP system. So essentially, the panels are fabricated, could be stored on site or could be stored at the plant, transported to the project, installed, post-tensioned, and then ready to open to traffic in very short order. The Roman, I'm just going to sort of contrast these three right here. The Roman stone system, which is a proprietary system, has, just like the Michigan system, has the dowel slots on the top, as compared to the Fort Miller system, where the dowel slots are on the underside of the slab. In the Roman stone system, the panel is installed first, and then the dowel slots are cut into the concrete, almost like, well, just like a DBR or a dowel bar restoration. Whereas in the Michigan system, the dowel slots are cut in the existing panel, and the dowel bars are embedded in the precast panel, and then when the then the panel is lowered into the dowel slots. In the Fort Miller system, as you can well see here, that the dowel slots and the dowels are fabricated into the panels and then sort of fitted together, along with this patented grout distribution system, which is has proven to be quite efficient in undersealing and undersealing of these precast panels. But nonetheless, these are some of the jointed systems that exist and have been used. The quick slab system was developed in Hawaii, and it's essentially a system where you have a series of slabs that are hooked together by a coupler system. So the joints are not active. The joints are essentially inactive joints, and you have expansion joints maybe every 60 to 100 feet. Another method that Shiraz had worked on was with the Port Authority of New York at LaGuardia Airport, where they use these precast panels, and these plates that you see are really the leveling plates in order to make sure that the elevation matching is done with the adjoining slabs on the runway. So this is sort of another way of making sure that the elevation of the new slab sort of matches with the elevation of the surrounding concrete. The Illinois system is very similar to the Michigan system or the Roman stone system, and so again, this is a test slab that they had fabricated at the Illinois Tollway. And some deflection testing, and this was really a proof of concept. The contractor had to get comfortable with how to install these precast panels. So this photograph is from the proof of testing, proof of concept testing at the facilities at the precast yard there. So those are some of the U.S. technologies that exist. Some of these technologies have been applied in Canada, but in addition to that, in the Netherlands, they developed what is called the Modi slab, and I'll show you some pictures of that. Some precast panel technology has been used in Japan, in Russia, in France, and then in Indonesia, most recently, and in 2008, Indonesia put down 22 miles of road using the PPCP system. And I think my understanding is that since then they have tried this at some other facilities with some level of success. So that is just amazing. They just went gung-ho with it and built 22 miles of it. You know, not 500 feet, not 1,000 feet. They said we're going to build 22 miles of the road. So that was a real testimony to this application and how technology can be exported from the United States to other parts of the world. This is sort of the French system where they're using hexagonal blocks, and I've been told that there is a fabrication installation guidelines that are available. These panels are typically 8 inches thick and about a 5-foot effective diameter, and these panels or these hexagonal blocks are installed over granular material. This is the Modi slab system. This was originally designed as a bridge roadway system over poorer foundations. Since then, the application has been extended to rail slabs, track on grades, roadways, and the concept was that you built about a 15-inch thick panel on porous material, and here's a picture, and you can literally see that water sort of flowing right out of the porous material. They've done some accelerated pavement testing on it, and they have put it on their motorways in Netherlands. So it is not just a lab. It's just not a lab product. It has been installed in the field. These are some pictures of the use of precast concrete pavements in Japan for street and highway applications. They also have some applications on airfields where they've used precast concrete pavements. So this technology is not just limited to North America. It has found its way to Asia and Europe also. And this is sort of a summary of what was done in the first project in Indonesia. It was built in 2008. This was a tollway in a very rural area, 22 miles, 4 lanes, 8 inches thick, and you can read the rest of the details. And I'm told that these presentations will be made available after the conference, so you'll get these details. But I was just stunned at the production facilities. I mean, this is just almost like an automotive assembly plant where they had to build all these panels and then transport them to the job site and actually install them. And so this was truly amazing, and this is what the finished product looks like in 2008. So clearly, modular technology doesn't have boundaries. If it's a good thing, we'll find a market wherever people are willing to apply and play with it. Some of the key considerations, and Professor Badenberg sort of mentioned these. Constructability is important, and it's not one size fits all. You have to really select the technology based on what the site can afford and what the site can withstand. Concrete durability is important, and why shouldn't it be? We have concrete durability specifications for our conventional concrete pavements. Why should we not have them for precast concrete pavements, be it jointed or pre-stressed? So I think that's important. But the key in a jointed system is really its load transfer and panel support. We've known this for many decades, that support conditions, and more importantly, the uniformity of the support conditions, are very critical in the success of a concrete pavement. And also the load transfer. How much deflection are you transferring from one side of the slab to the other? So everything that we apply to jointed systems should be transferred over to the precast concrete pavements. As Shiraz mentions, that these are not super pavements. It's not that because we are doing precast, we can put away and cast aside everything that we've learned over 100 years about concrete pavements and just assume that because this is precast, it'll all work itself out. No, it's not. We have to put in the time and the labor and the effort and the knowledge that we have to make sure that these considerations are taken into account for long life to actually take place. In order to get 40, 50, 60 years of life, you have to put in the effort up front. Once constructed, they just look like any other concrete pavement. So again, the takeaway is that these are not super pavements. We still need to put in the same level of technology and effort in it in order for long life to accrue. At least the projects that I've seen and visited over the last 10 or 15 years, construction windows are at night, and construction space is heavily constrained. So it has to be a really efficient, optimized operation. And in many instances, you probably get one or two lanes to work under, and the other lanes are still open to very active traffic. So it's important that there is good project management that happens, and in the pre-construction meetings, the plan is sort of laid out in order for successful construction to take place. Because otherwise you defeat the purpose of minimal disruption to traffic, because that is one of the hallmarks and the selling points of this technology is the minimal disruption to traffic. So again, management and lane closure requirements and all that are very critical when it comes to the installation of this kind of a technology. And this list is probably already outdated, but we've had projects using this technology in California, Colorado, Illinois, Iowa, New Jersey, New York, Utah, Virginia, and the list goes on and on and on. So a significant effort has been put in as far as the implementation of this technology has been ever since this technology has been implemented. So that brings us to this SHARP 2 project that was awarded to us about three and a half years ago. This was project R05. Shiraz Tiabji was the PI from Frugro Consultants, and I was the co-PI along with some other consultants and partner agencies. And as a result of this project, we developed, obviously, a final report with a series of guidelines for construction, for design, for installation, the approval process, and my understanding is that the final report was delivered to SHARP 2 earlier on this year. And we looked at all the applications that I sort of discussed and showed you up here in the first set of slides here. Basically, the systems that we addressed were the precast jointed systems and the precast pre-stressed system. The incrementally connected system is really a recommendation because we really don't have any field data on this. This is a suggestion. As I said, conceptually, this may have some promise. So I'm not going to read over this table, but this is basically the three kinds of systems we looked at. As part of the study, we also did some field testing of projects that have been already installed, and we looked at projects in California, Delaware, Illinois, Michigan, Minnesota, Missouri, New Jersey, New York, Texas, and Virginia, and these include both jointed as well as pre-stressed concrete pavements. And what I mean by field testing was that we did a performance survey, so essentially walked the pavement and counted the cracks, if there were any, and then we measured the deflection, and there was some ride quality information that was collected. And in order to do this, we needed the assistance of the state agencies to allow us to access their interstate system, and we are very grateful that they did that, and they allowed us to work with them. Without their assistance, we couldn't have collected this information and made it a part of the R05 study. And again, here's the laundry list of things that were delivered as part of the R05 project. Besides the final report, a series of these guidelines were presented. I've just been given the 5-minute warning, so I was talking fast. I'm going to talk really fast now. This is difficult when you're making somebody else's presentation. As I said, in the field testing, we looked at 6 projects that were intermittent repairs. We looked at 5 jointed systems, and we looked at 4 PPCP systems, and it was deflection testing, visual observations of distresses, joint elevation, and ride quality. Some of the testing was done at night, some of the testing was done at day. That just depended on how the access was made available to us. This is just some shots of the projects we visited. I think the Tappan Zee was one of the very first projects that Fort Miller worked on. So that gives you the longest time history on performance. The Minnesota is also about 8 or 9 years old. The Virginia project is a more recent project. This is more pictures of the Texas and the Delaware project. These are the PPCP projects that the team visited and looked at for performance. This is a project of some intermittent repairs in New York and in Michigan. And again, we found some distresses in the Michigan project, and the 2 pictures that you see, one is a perfectly working panel since it's about 12 years old, and in the same demonstration project, you see one panel with some distresses that are concentrated around the dowel slots, and we can talk about in the Q&A portion about what we think caused those distresses to take place. But this sort of gives you an overview of our projects that are about 12 years old. At least the Michigan project is about 12 years old. For the most part, the performance of all these pavements was acceptable and actually beyond acceptable. Both in terms of deflection testing as well as in terms of very little distresses that we observed, both for the jointed system as well as the precast as well as the pre-stressed precast systems. Well, I've talked about the guidelines here. I think Ernie mentioned about the importance of load transfer systems, and I can't emphasize that enough. It's not only designing how thick the dowel should be. I mean, the diameter of the dowel bar is tied in with the thickness of the slab. There's clustered dowels as well as you can have full width dowels, and usually for intermittent repairs or full depth repairs, we've been using cluster dowels, that is either 3 dowels or 4 dowels in the wheel path. For continuous type of repairs, traditionally we've been using full width panel dowel bars. But nonetheless, however you are installing dowels, whether it's cluster or whether it's continuous, we still need to be aware of the dowels need to be aligned. We can't have misaligned dowel bars, because if you have misaligned dowel bars, the joints are going to get locked, and then, of course, you're going to lose the pavement. We need to make sure that we are measuring you're getting adequate load transfer efficiency, but more importantly, you're also you're keeping the differential deflection across the joints low, because sometimes load transfer efficiency can be misleading, but differential deflections is the real deflection that you're seeing between one side of the slab and the other side of the slab. So that's important. That is mentioned, that is kept in mind when it comes to design. I'm going gonna skip some of this stuff. The other important piece is the base support. It has to be uniform, and the base has to be stable, because if that doesn't happen, you are going to get point loads or some sort of tenting, and you can cause cracking in the concrete panel, and then of course you've lost your repair. Several types of bases have been used, as I've alluded. You know, you have granular bases, you have asphalt stabilized bases, cement treated bases, lean concrete bases, and then of course we've had use of pervious concrete bases, rapid setting lean concrete bases. So there's a whole gamut or suite of bases that have been used. But the takeaway is make sure that the base is uniform, the base has the right structural capacity, and it provides the needed support for that concrete pavement to last, whether it's a jointed system or whether it's a pre-stressed system. Because if you recall, in the pre-stressed system, the slab is thinner. You're replacing maybe a 12-inch slab with an 8-inch or a 9-inch slab. You're getting the fatigue resistance because of the pre-stressing, but because you've reduced the thinness of the slab, there has to be deflection resistance, and that deflection resistance is going to come from the uniformity of the base. So if you compromise the uniformity of the base, you've lost the advantage of that pre-stressing. And the savings of the thickness. So again, you know, this is Pavements 101, and we really have to make sure that we apply that to this technology also. I just mentioned about the thickness savings in the pre-stress. These are about 3 to 4 inches thinner than conventional cast in place. Because of the pre-stressing, you're taking advantage of the pre-stressing and helping the fatigue life. But again, the deflections need to be looked at really carefully. Well, I've already told you about the advantages, so I'm not. I'll just conclude with some of these refinements. Traditionally, the dowel slots have been about 3 inches or 4 inches, and if these dowel slots are not backfilled prior to opening of traffic, we've seen some problems. We've seen some breakage of these dowel slots. And so one of the refinements that we are suggesting as part of the R05 is sort of a narrow mouth dowel slot, whereas it's about 1 inch opening on the top and about 3 inches at the bottom, and the dowels can be slid in. And again, this hasn't been tried, but it has a potential. Conceptually, this should work. So this may eliminate the fact that you have to grout the dowel slots immediately after placement, and you could probably wait 24 hours even after traffic has been, even after the pavement has been open to traffic, and you can come back and backfill. So this is something that we can look into. The other refinement that I talked about was this incrementally connected panels that are individually pre-tensioned and then connected with deformed dowels. So you have inactive joints, and then every 60 or 100 feet you have active joints. So again, this is a suggested refinement, and field trials will prove whether this is a valid refinement or not. Refinement third was sort of how do you repair CRC pavements, and one of the challenges is the continuity of steel. And my understanding is that in South Carolina they have used cast in place full depth repairs to repair CRCs and not used steel continuity. That may be so we could use a precast panel as a full depth repair and not use steel continuity. Again, we haven't tried this. This is some borrowed information from South Carolina DOT. I'm going to stop here in interest of time, and then of course I'll be happy to answer questions after the official workshop is over. Thank you.
Any questions for Professor Bush? Go ahead.
Regarding the papers that France using taxonomy,
Yes.
Two questions. One is, why is the thickness so big, 17 inches? How do the joint load transfer, how does that perform?
This is outside my comfort zone, so I'm really not sure how they're installing this hexagonal, unless somebody else in the audience knows how these hexagonal panels are being installed. My understanding is, again, the way they're using this is that they flip them around also. So once one surface has been used, they actually flip these panels around and reuse it. So it has two lives out of out of the same panel. And I know they've been doing this in urban streets. And especially where they have these utility, for utility cuts and all that. So this is more convenient in urban areas in France. But unfortunately I can't answer your question about from an installation standpoint unless somebody in the audience has firsthand knowledge of how this is done. Yes.
Have you executed any operation on the runway with few hours closure time?
Could you repeat the question, please?
Have you executed any operation on the runway?
Overnight runway construction.
Yeah, as I showed you an example, I personally haven't, but Dr. Tayabji, and I know Dr. Brandenburg has been involved with airport projects, but the Port Authority project that I showed you, or at least I showed you 3 pictures of, that was an overnight construction. Whoa. That was an overnight construction, and it was successfully completed under a very constrained window. This was at LaGuardia in New York City. But I'm sure Professor Brandenburg can give you many more examples than LaGuardia.
Dulles Airport.
Absolutely.
All of them have done that, and in fact, I think the contractor that did the Dulles Airport is here.
Oh, okay.
They can talk about that one.
Okay.
So, yeah, it has been done, can be done, very effective.
My name is James Bryant. I'm with the Sharp 2 program, the lead staff in the renewal area, and I just wanted to comment that the final report and guidelines should be out by the end of the year. They're actually going through the publication and editing process now. And one slight, I guess, advancement is that we have actually used the narrow mouth slots at the Illinois Tollway Authority. They've placed it in a couple of trial sections. The contractors really liked it, were able to work with it, and in fact, the Illinois Tollway Authority is constructing about 700 or 800 panels to use for intermittent repairs there.
Well, thanks for
So
the
it has been
update,
done.
James. Thanks.
Thanks a lot, Professor Bush, for your excellent presentation and for replacing, of course, Shiraz in a short notice. Ah, yes, but you have done a great job.
I
Second. All right, our next speaker, Tom Kazmierowski, has over 30 years of experience in pavement investigation, evaluation, design, management, construction, and rehabilitation. Currently, he is the manager of the office responsible for materials engineering and research within the Ministry of Transportation of Ontario. He has served as a committee member, co-chair, and chair of numerous national and international technical association, boards, and industry-sponsored events. He will present to us the MTO perspective on precast concrete pavements in Ontario. Tom, just maybe try to. Are you okay with the board? Yeah, I have this. Put it on.
Oh, there it is. Now we gotta get this cleared up here.
Sorry. Oops. Not sure it will work. Well, we'll do that on the next then. I'll let you go with this. Sorry.
Good, thanks very much. Merci, Denis, and good morning, everybody. In recent years, Ontario's Ministry of Transportation has completed a number of precast concrete slab repairs on heavily trafficked highways. The placement of our initial trial sections were presented at the Saskatoon Transportation Association of Canada conference in 2007. The following presentation will highlight our 7 years' experience with precast concrete pavement repairs on Highway 427 in Toronto, and reflects a paper presented at the 2011 TAC conference in Edmonton last year. MTO carried out the first trial of precast concrete slab repairs in 2004, and the performance has been monitored annually. The trial was located on Highway 427, which is a major freeway through Toronto. There are 3 types of precast concrete slab methods demonstrated on this trial project. They are the Michigan method, the Fort Miller intermittent method, and the Fort Miller continuous method. Traditionally, MTO uses fast-track concrete mix repairs for heavily trafficked urban locations, and it's carried out overnight due to closure requirements. But the fast-track method is problematic, and the long-term durability is quite questionable. That's why we're pursuing alternative repair methods that do not require a long closure time and provides a good quality product. Precast concrete seems to address these issues by ensuring better quality concrete, better curing conditions, minimal weather restrictions on placement, and reduced delays prior to opening to traffic. Let's look at these trials from 2004. This slide shows the precasting of the Michigan slabs. Note the 3 bars per wheel path installed on both sides of the precast slab. Placement of the Michigan method involves saw cutting the removal area and then lifting out the concrete that needs to be replaced. Next, the slots for the dowel bars are sawn in the adjacent slabs and chipped out, followed by the base being partially excavated. In this case, the base material was a cement-treated base layer, or a CTB. Then cementitious flowable fill was placed and leveled using a manual screed in this case. The new precast slab with the dowel bars already cast into the panel was then carefully lowered into place, as you can see in these 2 pictures. The grout was then manually poured into the dowel bar slots to complete the installation, and this typically it's a proprietary grout, non-shrink rapid set. The following slide shows the performance of the Michigan slabs between November 2004 and when the slab was first placed and October 2009. This slide shows a completed repair using the Michigan method immediately after construction. Here we see the precast slab in June of 2005 after 1 winter's exposure. In 2006, after 2 years of service. In September of 2007, you can see the visual, the visual survey indicated 2 of the 3 trial slabs were showing distress in the area of the dowel bar slots, and Niraj showed a similar picture, deterioration around the actual slot area. In 2009, the survey indicated that only 1 of the Michigan slabs of the 3 were performing well, with no distress at the dowel bars. With this trial, we learned that exercising care during concrete removal of dowel slot locations can prevent early cracking around the dowel bars. And this is a theme that keeps on coming up. You know, this isn't rocket science installing these, but you got to do it properly. And if you don't, you're going to see problems occurring very quickly on some of these projects. In the 2004 trial, 3 precast slabs were made for the Fort Miller intermittent repair method. Note that this method has 4 blockouts cast for dowel bars per wheel path. Placement of the Fort Miller method involves saw cutting and the removal area, then lifting out the concrete and partially excavating the cement-treated base. The pavement structure at this site was basically 9 inches of a plain jointed concrete slab on 6 inches of a cement-treated base. Pavement was constructed back in the late 60s, early 70s. And the thickness of the slabs was somewhat variable. So although we assumed a certain thickness, when we actually got out there and started removing, we found varying thicknesses. So it was required for us to actually remove a bit of the cement-treated base. The cement-treated base did not come up when we removed the slab. Some people have experienced that. I think Caltrans has that. They were actually pulling up the cement-treated base when they removed the slabs. That wasn't our case.
Very rarely,
Sorry?
very rarely.
Very rarely. That wasn't our case. It came up fairly cleanly, but we had to scrape or remove a bit of the cement-treated base to accommodate the fill material. After removal, the next came placing the fine-graded crusher run screening material and compacting of the base. A precision grader, here we used basically a manual scraping or grading tool. A precision grader would be preferable to the manual screed shown to ensure the accuracy of the base here. A template was used to ensure dowel bars were being drilled in the proper or the matching location. Then the contractor drilled holes using a gang drill to install the dowel bars on the face of the adjacent slabs. This slab shows injecting the epoxy into the holes and the installation of the dowel bars. And next, the Fort Miller slab was lowered carefully into the excavation. After the slab is placed, bedding grout is pumped into the grout holes, with the grout flowing evenly between the slab and the base to ensure uniform support to the slab. Also, dowel bar grout is pumped into the holes to ensure the dowel bars are secured into the new slab. Now the following slides show the performance of the intermittent method between November 2004 and October 2009. This slide actually shows the completed repair immediately after construction. The next slide shows the Fort Miller precast slab in June 2005, which has been exposed to one winter of traffic, and we're doing some falling weight deflectometer testing there at the time. Here we can see the precast slab in 2006 after 2 years of service. Certainly the Fort Miller slab is performing very well. 2007 after 3 years of service. And here we see the Fort Miller precast slab in October 2009, which was taken after the slab's been in service for 5 years. The slabs are performing well with some very slight hairline cracks noted over some of the dowel bars, and that might be a result of just non-uniform support in that area. The third trial in 2004 included the Fort Miller continuous method, where interlocking precast panels were formed for a total length of 25 meters. Dowel bars were installed on one side of the repair and blockouts on the other side of the repair. The excavation for the continuous method is similar to the intermittent method, which requires saw cutting the repair area and lifting out the existing concrete. This was followed by partially excavating the cement-treated base again to ensure that we got proper thicknesses. Next involved the placing the fine-graded screening material and compacting the base. Again, a precision grader would be preferable to ensuring an accurate base elevation, and it wasn't available at this time, being our first trials. Compaction is then followed by gang drilling at each end of the excavation and epoxying the dowel bars into place. Then the Fort Miller slabs can be placed into the excavation one after another in a sequence similar to basically interlocking pieces of puzzle. This slide shows the placement of the slab, number one of 6 slabs. Denis was concerned I had over 60 slides, and he said, "You're never going to get them done in 20 minutes. Well, this is why I had so many slides. Placing a slab 2, placing a slab 3, placing a slab 4, 5, and 6. So those were that was a continuous trial that was placed. The final step was to inject the bedding grout and dowel bar grout to complete the installation. Again, these following slides will show the 5-year performance of this continuous slab trial. This shows the final product immediately after construction. Looks great. Here we are after being exposed for 2 winters of traffic. A view of the trial in September 2007. These trials put on heavily trafficked freeways. It's so difficult to get out there and actually take a look at these sites. And you sort of take whatever window they give you. Usually it's a Sunday morning. So unfortunately, we're missing mass going to looking at these trials. Certainly, the final slab shows 2009, which were taken after 5 years of service. The slabs are performing well, with slight hairline cracks noted over the dowel bars in a few locations. As I mentioned earlier, these slight hairline cracks probably are a result of some base support issues, probably reflecting the lack of a proper grading of that base. So looking at some recent contracts, those were our, as Niraj referred to them yesterday, he called them the onesies and the twosies and the threesies. Those were our demonstration trials. We tried it. We were fairly pleased with the results. Obviously, there were issues, but we're quite prepared to move forward. So we did some recent trials in 2008 and 2009. Let's refer to them as Contract A, which involved a little over 1,300 square meters of precast repairs, and Contract B, which involved close to 1,700 square meters of precast. This is not equivalent to the 22 miles of work that was done in Indonesia, but for us, it was a pretty good step forward. Lessons learned from the trials in 2004 were implemented on these contracts. There were several that were put in, but I'm just going to highlight a few of them. This contract utilizes, I think this is the major change, a precision grader from the Fort Miller method. I think, Peter, you just had developed that precision grader at the time, and certainly that was very handy on these contracts. This is a close-up of the precision grader used to level the screenings for the proper elevation. Here we can see the compacting of the screenings and final grading. And this slide shows the lowering of the precast slabs. Now you can notice something a little different. We now have blockouts across the full face of the slab. Now we had 300 millimeter or 1 foot spacings. This is to ensure uniform load transfer across the full width of the joint. It's something we realized when we were doing the FWD testing that we wanted to ensure we had good load transfer across that face. Here we can see the contractor carefully placing the Fort Miller slab into the excavation. Again, a view of the Fort Miller continuous slab method. And we can see this slab has dowels all the way, again, across the face of the slab versus the 4 dowels in each wheel path in our initial trials. So some observations. Contract A was carried out by the same contractor as the 2004 trial, and the slab placement went very well. If you've ever been out to the site, this is like a continuous assembly line of work. If it's being done properly, it looks great. You need to make sure that things are operating properly and this assembly line continues to work smoothly. Initially, the contractor was slow in setting up the precision grader, but once the contractor got up to speed, the process went very efficiently. Contract B also implemented the precision grading. This was the first time this contractor had experience with this precast slab installation procedure, and as Dr. Beringberg said, it would be nice if we certified some of these contractors to do this work, but and you'll see why very shortly. Contractor B had put a lot of effort into achieving the proper grading and using the precision grader. Most slabs were flush to the adjacent pavement. However, there were other issues with this contract. The contractor overcut the slabs, which created gaps between the slabs, and sometimes the slabs didn't fit. Spalling occurred during cutting, removal, and placement of the slabs. And also some of the slabs were not grouted immediately and left up to a week before grouting, which caused many of the slabs to settle, crack, and small. So it was mentioned that you might get away with leaving them ungrouted for 24 hours, but I suggest you don't leave them ungrouted for a week. Imprecise saw cutting meant that sometimes the slabs didn't fit, and you end up breaking the back of the slab. What did you say yesterday, Niraj? Measure twice, cut once. I think that's the old rule of any carpenter. It also holds true for removal and placement of these slabs. Tight spacing resulted in spalling during installation, so you can see the spalling occurring. Spalling adjacent to the concrete occurred during removals, where they're sloppy in taking out the existing cut panels. Gaps were present between the new and the old slab due to overcutting. Settlement issues arose when slabs were not grouted immediately after installation, and some slabs were not grouted for up to a week, as I mentioned earlier. And this is pretty ugly. The settlement issue led to spalling of the concrete over the dowel bars. You can see it actually popped the concrete off and exposed the dowel bar and a little bit of the reinforcing. And a few longitudinal cracks were also identified on the precast panels. These cracks probably resulted from not immediately grouting the slabs in place and allowing them to rock and crack. So contract B, in summary, there were installation issues, as you can see, and it resulted in the performance repair panels that did not quite meet expectations. Some slabs showed transverse cracking, longitudinal cracking, and spalling. The work was halted while the contractor reviewed the operation and prepared a proposal on how to continue. After the operation was shut down, improvements were made by the contractor. More care was taken in saw cutting for removals, since the spec requires the contractor to replace the damaged slabs at his own cost. Also, the grouting operation was carried out much sooner to prevent the slabs from moving, which led to the cracking and the spalling. The slabs placed after the shutdown were inspected thoroughly and found to be in good condition. So, in conclusion, precast concrete slab repairs can be placed efficiently and effectively, and is a good alternative to fast-track repairs. However, care is required in every step to ensure a quality final product. So, as it was said, I believe mentioned yesterday, it's all in the details. Saw cutting, removals, base preparation, slab placement, and grouting all are critical to the success of these precast repairs. MTO continues to specify precast slab repairs with 2 new contracts incorporating these repairs awarded in 2011 and carried forward into this year. That's it. Thanks very much. Any questions at all? Yes.
Are the dowels fixed from both sides, from one side in the epoxy and from the other side into the grout? I correctly understood?
Yeah, typically when you're doing individual repairs, just individual slab repairs, you fix them both sides. If you're doing continuous repairs, you have one side a block and one side a dowel bar.
Because in the conventional pavement, we fix them from one side and we cover the
I
other
see what
side
you're
with
saying.
grease
Actually,
in order to slide.
Yeah, I see what you're saying. Yeah, no, they use smooth dowel bars on both sides. There was not, basically a reinforcing bar on one side and a smooth dowel on the other.
Thank you.
Any other questions? Yes, in the back?
Andrew Lotz from Cape Town, South Africa.
Oh, yes.
With regard to debonding of one half of each dowel and a end type movement allowed for the one half, I didn't hear any details on how you install those things during these repairs.
Debonding of the...
Debonding of one half of a dowel,
Right.
and allowance for an end movement on one half debonded.
Yeah, we did put a bond breaker on the bars themselves that were exposed prior to placement. We didn't experience any. If you're talking about lockups, we didn't experience any issues with lockups.
Okay. And no end caps.
Not in these instances. No. We don't see these as being expansion joints necessarily. So we didn't really experience any issues associated with that. No, there are no caps involved.
We normally allow for a thin disc at each end of a half dowel, just to allow for a millimeter or two of movement, a foam type disc.
Yes, I understand what you're saying, and typically we'll do that with our expansion joints and new construction, but that isn't the case here with these repairs. Yes, Dr. Barron.
Hi. Would like to know if after the installation, would like to
Your
know
voice
if
changed.
after the installation, if you have to grind the surface or the crown.
That was called for in the specifications, and I think that's a good idea because regardless of how careful you install these, you often get a slight elevation difference on the surface. Now, keep in mind, these were repairs that were then scheduled to be overlaid. It was part of that was part of the whole freeway system, repairing the existing old concrete pavement and then putting a two-lift overlay on top. In fact, the old two-lift overlay was removed prior to doing these repairs. In the past, we would have just cut them out and put in a fast-track repair. So if it was an exposed concrete surface, yes, we would have diamond ground it. In this case, since we're putting two lifts of hot mix on top, it wasn't that critical.
Most of your repairs are done at night, so it didn't become an issue, but like a weather we had this year was so very hot. If you tried sawing those in any time except at night, and maybe even at night, do you have any problem with the expansion of the concrete binding up the saws and this sort of thing? And did that have an effect on the spalling of the removal of this sort of thing?
It's a good question, because in the past, we've actually experienced where we had the binding of the saws on the fast-track repairs. We didn't experience any of that on these repairs, and that could have just been a function of the weather conditions. I mean, our trials were done in was it November, I think, Peter, if I'm not mistaken? It was certainly late in the year. Terrible weather, raining, cold, it was cold, and they still work. But you're right, once on the heat of the day, this road in particular has been notorious for blow-ups because of that. And certainly these repairs have addressed some of those concerns. Any other questions? If not, thank you very much.
Thanks a lot, Tom, for sharing with us your MTO experience. For sure, for your neighbor province, this is very inspiring. So hopefully that the people from my province in the room will learn about your experience. All right, our next speaker and last speaker before the break is Mr. Scott Nussbaum. Mr. Nussbaum has worked for Utah DOT for 15 years and has experience in construction engineering, operations, pavements, and materials. He is a graduate from Utah State University, is a licensed professional engineer in the state of Utah, and is a certified public manager. He was instrumental in implementing precast paving in UDOT, including Region's first project on I-15 in 2009. He will present to us Utah's perspective. Scott, the floor is yours.
Thank you. I thought as I talk today, I'd probably spend a little less time on technical aspects of what we're doing, and maybe just give you a little bit more from kind of a Utah perspective, why the Department of Transportation is doing what we're doing, and kind of the success that we've seen. We've done a number of projects so far. So I kind of want to give you a little bit of a history and kind of a perspective, so you can kind of understand how precast pavements fits into our philosophy in Utah, which might be a little bit different. We'll go over some of our experience, but again, I'm not going to get into a whole lot of technical details, just kind of give you a flavor for why we're doing what we're doing. And the big question that I'd like to give you my answer to is, why should the concrete pavement industry care about precast pavements? How that fits into the overall picture in my mind. So, the Utah Department of Transportation, we're a little unique in some ways, I think. We have some advantages and disadvantages where we're at, but just so you understand where we're coming, we have 4 drivers within the department. These are a mission statement, if you will, but it's kind of ingrained in our organization, and we kind of understand what those are. The first one is that we preserve infrastructure. We're focused on that. We understand that we need to take care of what we have. If 20% of the slabs are broken, if we can do things to preserve what we have rather than replace the whole thing, we're better off in the long run. And precast slabs kind of fits into that strategy. We believe in optimizing mobility. We do some unique things with diverging diamond interchanges and continuous flow intersections and some of those kinds of things. Sometimes we need to add lanes, but we're trying to get the most we can out of the system that we have. That falls over into construction as well. Maintaining mobility, keeping traffic moving during construction, those kinds of things. We are focused on safety. We're concerned, you know, like a lot of us, as we improve, we're doing better. We've had almost a 40% drop in fatalities since 2000, but we're concerned about the public, and we're concerned about our workers, and we're concerned about the exposure during construction. And this is something that I think might be a little unique, but for us it's really important. In Utah, we believe that our transportation system is essential to our economy, and we're focused on that, keeping goods and service moving. And I'll explain a little bit why that is. Back in May of 1869, the Transcontinental Railroad was completed in Utah. And they drove the Golden Spike as the railroads from the east to the west and the west to the east came together there in Promontory. And we kind of picked up this moniker, hey, we're the crossroads of the West. But that continues to be true today with highways. Much of the commerce in the United States going back and forth east to west goes through Utah. We have the highest percent or composition of truck traffic on our highways as any state in the union. We have a lot of truck traffic. 23% of our traffic is truck traffic. And so when we're out there rehabilitating concrete pavements, we want to keep that moving. We don't want to slow that down. We believe that has an impact on the economy, and we're willing to spend a little bit of money up front to make that work. So as we talk about minimizing impacts to traffic, it's part of our culture. We do some fun stuff. Last year I was out there as we moved the Sam White Bridge, built off the side of the freeway, 108 meters long, 354 feet long, two-span bridge, all in one piece, built off the side of the roadway, and then moved in place overnight so that we could keep traffic moving underneath. And, you know, that's kind of a big, spectacular thing. It's much funner to watch on time-lapse video. It's a little like watching paint dry during the night, but we do some of those things that are fun and big and spectacular, but precast pavements kind of falls into the same kind of philosophy for us. It's a process for us to be able to go in and get what we need done and get things open to traffic the next day, so that in a lot of ways the work that we're doing is invisible to the traveling public, and everything keeps moving. So a little history in Utah. Our first project was back in 2006, and I was not involved with this one, but I was aware of it. We had an engineer by the name of John Butterfield who said, why do we need to worry about some of the durability issues we're seeing with fast-set concrete repairs? Why do we need to worry about this cure time? There ought to be a way that we can go and do this. And so, not taking advantage of a lot of the information we have today, there was a project that we put together. 34 slabs went in to replace broken slabs on I-15. They started after the rush hour on one night, went into the next day, put these down. They put them on a sand leveling course, no grouting underneath, dowel bars and tie bars both directions. The picture that you see here was kind of a cluster. Most of these were 1 and 2 slabs at a piece. It was very expensive for us. We spent a lot of money on those slabs, and there were a few slabs that didn't work out really well. What the primary failure was ended up being our dowel bar connections. And there were some interesting things that we figured out looking back at the pictures later. We didn't quite remove the curing compound from the slots that were cast in the precast slots, and so we had a bonding failure there. So we had a few slabs that broke. We had a couple that started rocking right after construction, and but for the most part, they look good. This was taken just last week. That's that same location, and those slabs are looking very good. There's not one of those that's failed. Out of the 34 slabs, I think there were 5 that had some problems, but they weren't catastrophic failures. In fact, they remained in place until just a couple of months ago when they were replaced with new precast slabs. So, but we did have some issues. We spent a lot of money up front, and there wasn't a whole lot of momentum coming out of that project for the next project until we started really seeing the increase in traffic and some of the things that we have as congestion increases in some of our areas, and we started looking at this again. So this is where I got involved with my first project. We were planning a traditional rehabilitation project on I-15 near Hill Air Force Base. It gets a lot of traffic. And our rehabilitation projects, we turn around projects really quick. A rehabilitation project gets a few weeks in design and it's advertised. But we had some discussions about, hey, you know, we need to look at this a little different, because how are we going to actually be able to cure concrete and keep traffic moving through this? Well, things didn't get slowed down like they were supposed to, and we got this project advertised, but understanding the ramifications, but you know how the materials folks don't always talk to the traffic folks and everything else. Well, we got a project that went out, traditional repairs, but said you've got a 5-hour window from when you put the first barrel out to when you get it off at night, and we need you to repair that. So I started getting the phone calls from the contractors as the advertisement went out. This was kind of the first time I was aware of it, saying, hey, what kind of concrete can we use? What are you going to allow us to put in place? And understanding some of the durability issues that we have with high early strength concrete, we pulled that project back. And maybe I ought to just tell you a little bit about our concerns with high early strength concrete. I believe that high early strength concrete is a product that can work, but we are in a climate in Utah, it's not real cold, but during the winter, we freeze and thaw every day, sometimes more than once on our pavements. We have what we think is the greatest snow on earth. We advertise it that way for skiing, but we don't like it on our roads. And we put down a lot of salt to keep our roads clear. So we got high chlorides, a lot of freeze-thaw environment, kind of a worst case for durability in our concrete pavements. Some of our traditional repairs that we've done, you know, we spend a few days to get it up to strength and open it up, but our patches, even when we have, you know, 4 or 5 days or a week to cure out, a lot of them aren't lasting 5 years, and they're cracked and broken and need to be replaced again. Some of them do a little bit better, but some of them do a little bit worse too. So we haven't had a lot of success. And then so as we look at this and trying to shrink things down to a 5-hour window, just didn't work for me. I was really concerned about all the risks there, opening to traffic. You use these mixes, and they're highly sensitive to temperature changes, and we're doing this in projects that extend through the spring season, things like that. So I wanted to do something different, so we went back and kind of revisited that project from 2006, and understanding that, you know, a little bit of bedding grout would stabilize these slabs so they wouldn't rock. We can pay attention to the connections, and we can probably have something that's going to work. So I kind of sold the concept, and then the project got advertised without a whole lot of the preliminary engineering. We're just getting a little fast, I think, but gratefully we ended up with a supplier that knew what he was doing, and a contractor and a precaster. When I said supplier, I meant the supplier of the technology, but and a precaster that were willing to learn and do a good job. And it actually ended up being a great success. Every one of those slabs is intact. They look good. Not a one of them's cracked. And it was a significant project, 3,100 square meters. About this time, our department was kind of getting up to speed and saying, hey, we're really good at accelerated bridge construction. We need to look at accelerated pavement construction. How can we do that? And a scanning tour was organized where we came back to New Jersey and Delaware, where we're doing some of this stuff, and to look at this. We brought our contractors, we brought some of our consultants, as well as our DOT people. We brought some of our precast suppliers to come out and say, hey, is this something that can work? So while this first project is going on, and I'm really nervous about how it's working, we got out to kind of see some of these things that were going on and where things were working. It gave us a good deal of confidence. And we started thinking, hey, you know, I was thinking, hey, maybe my job is still intact. Maybe this is going to work. So we just kind of pressed ahead because things were working. We advertised another project, this one not quite as big, but again, on a critical corridor, on I-15. Different contractor, same precast supplier and same technology, but we didn't actually specify the technology. We left that open. And through these contracts, we developed our own generic options as well. We got that project out, and then as a result of that scanning tour in the region to the south of me, they had a Highways for Life demonstration project, and this was completely different. The Department of Transportation worked with Thailand to come up with a generic option. This one, they put down steel plates in the four corners where they're dropping the slab in, and they had leveling screws. They put the slab in, turn the screws to level it in place, and then fill the void underneath with a urethane grout. Kind of unique, and it worked pretty good. There are some hairline cracks in those slabs, but for the most part, they look good. And with the reinforcement and everything else that's in them, we're not overly concerned about some of those small cracks. So that's working pretty good. 56 slabs, those were pretty much continuous in that project. Region 2 did another little project, and you'll see that their projects are small, ours are big. I don't know if they have a better grasp of the risk, but it just reflects the confidence that we have in how things are working. Then this is probably a significant one. This has been our biggest project to date. As you can see, 10,400 square yards, or 8,700 meters squared, intermittent repairs, but a lot of these are close together. The significant thing about this one is they used a generic option. Now this generic option is one that we had designed on paper there in Region 1, just kind of thinking, as Tom said, that this isn't really rocket science. We can make this work, taking advantage of some of the ideas that we have from the AASHTO TIG and some of the work that had been done. We had a simple generic option in there, and they actually installed it. This was one of those projects, and every contractor has them, every agent. Nothing went right with this project. It was a Dalbar retrofit project. The whole length of the freeway was being retrofit with Dalbars. Things didn't work very good. So I got to spend a lot of time out on the project and watching what was going on. We didn't have a lot of problems with our precast slabs. The biggest thing so that experience on a tough project probably helped me more than anything with my confidence. Because as we were out there looking and saying, okay, what do we need to do differently? What do we need to learn from this experience? Really what we came down to is if we pay attention to the specifications and we pay attention to workmanship, this works. It works. And so right now they're performing pretty well. And we're excited about where we're going, even though we had a lot of struggles on that project. A lot of that with the Dalbars. The Dalbar connections on this one, since it was a Dalbar retrofit project, we just put the Dalbars in the same way, sawed them right into the pavement as we went, and just kind of staged that so that we weren't leaving them without those Dalbars for very long. So we've continued to do more projects. We had another one down there in Region 2. Moving into this year, we've got another significant one on I-15, 200 South, I-84. This is section north from our first project in Region 1. It's underway, and they're casting slabs today and placing them tonight. We've got some smaller projects going on in Region 1. So right now we've got 3 projects, active construction projects with precast slabs. We also have a permit project where we had a pipeline come in and damage a portion of our interstate. The problem with this one is most everything we've been done has been putting things in pavements that are 40 years old. This pavement that was damaged was 2 years old, brand new pavement, damaged by a pipeline project. So we're beefing up our designs just a little bit and paying a little more attention to detail, but their repair, we've required them to put in precast pavement, and they're using an experienced supplier to do that. And this is one on some of these others. We've just hoped to get enough life, and if it lasts twice as long as a cast-in-place repair, we're doing great. This one, we're hoping that we get 40 years out of or more. And Thank you. I appreciate the 5-minute warning, and I'm getting really close. One thing that is people have talked to me, they ask about cost. And this is a big deal for us. Our initial projects were very expensive. And what I've got here up on the chart is kind of over time, our costs per square yard, which is how we bid those, and in many of these cases it includes the grinding and everything else that we specify as well, compared to cast in place. Now, I'll admit up front, the difference is a little artificial, because we all know that costs in a high traffic urban area, construction costs are higher. We're not doing the cast in place repairs in those environments. We're doing it where we've got time and leniency and those kinds of things. But we started out with pretty high cost. Now, I think nationwide, we're actually probably doing pretty good. I think we were $423 a square yard with the first project that we did there in Region 1 back in 2009. Our recent projects have been on the order of $200 a square yard. So we're seeing a downward trend here. Also, if we took into account what it would cost if we were doing very highly strength concretes, some of these proprietary mixes and those kinds of things, that increases the cost of cast in place as well. So we're seeing a convergence of those costs, which is actually a little bit surprising to me. But for the value, so there's a cost difference. It's decreasing for us, but there has to be a value for that. And this is kind of the value we see in it. The biggest thing and the driving factor for us is minimizing the impact of traffic. This allows us to do it, and in my mind, it mitigates the risk. Something goes wrong, you can still drop that slab in there, you can shim it into place, and you can open traffic on it, because everything we're doing in Region 1 is slab on grade. And it mitigates the risk. Say somebody drops the slab and breaks it. Well, we've got a precast yard with all these slabs. We're keeping them uniformly sized for the most part. We've got a spare that we can drop in place. We've got a means to get things open to traffic the next day, and we can address it the following night. When a mix goes bad, a set retarder doesn't get added at the right proportions, those kinds of things, you can't open to traffic like that, and you're in a mess. So it mitigates the risk for us and helps us open to traffic. Ideally, there's a lot of other benefits. We're putting a reinforced slab, and it's just really reinforced for handling, but we've got a reinforced slab in there now where we did not have a reinforced slab before. If we had a base support issue, that's going to help us, right, for the long term. We can cure these in a precasting yard, supposedly under ideal conditions. We can put a water cure on them for 10 days, decrease the permeability of the chlorides and those kinds of things that we see in our state. There's just a lot of advantages. Being able to do things in a controlled environment rather than out on the freeway at night just should give you better quality control overall. So in the long term, we're probably putting down something much better, even though our primary driver is minimizing impacts to traffic. So for us, it's a tool in the toolbox. I think you'll continue to see us do this as we are trying to maintain freeways. Our interstate system was built in the 60s and 70s. It's an aging system. We're not able to replace it all, and we want to preserve it and extend the life there. And so we'll continue to do this. There are places where we wouldn't do it. If we can afford to close a lane and do a cast-in-place repair, allow it to cure properly, that is the way that we would go. But where we can't afford to do that for traffic, we won't. And so why do I think the concrete pavement industry should care about precast pavement? The precast pavement technology increases the serviceability and extends the life of a Portland cement concrete pavement. It makes it more valuable. It's a tool in the toolbox. For our maintenance folks, having to replace blow-ups and things like that and these repairs, it's a headache, and we haven't had a whole lot of tools to do it. We get asphalt patches out there, and then those don't hold up. This is a way that we can replace those sections of the pavement that are failing and preserve the life of that investment. So I think I'm out of time if I'm monitoring that close. So are there any questions? right, thank you.
So thanks a lot for your excellent presentation. Just remind you that this workshop is sponsored by National Precast Concrete Association. Just a little word before the break, it's still time to register for the technical visits on Thursday afternoon. We will take a break. After the break, we'll still have 3 excellent speakers that will talk about the precast concrete pavements. So we'll take a break 20 minutes. Be back please at 10:20. Thank you.